Okay, in this video, we're going to continue. This was the previous video. We figured out the length of a rod using this approximation using the average temperature. And so that begged the question, how would we figure out the exact result? Because what if this, yeah, we know the temperature is constantly changing in this problem. So how is that going to affect the result? Let's go ahead and take a look over here on board 2. All right, and so here's what we started from in the last problem. We said that the power was dq dt is Ka delta T over L. Now the tricky part here was delta T was constantly changing. It was initially 80 degrees, and then eventually it became 79, 78, etc. So the change in temperature between the hot reservoir and the cold reservoir was constantly changing. How can we figure out this temperature as some function, and what function should it be? Well, I do know the following. I know that if I apply some amount of heat to the ethyl alcohol that has mass M and C, specific heat C, the temperature final should equal, should be related to this. The ethyl alcohol started at 20, it had some mass, some C, and this would give you the final temperature of the ethyl alcohol if you applied some amount of Q to it, all right? If we rearrange this and solve for T final, let's see what we get. Oh, you know what? I'm going to rearrange it this way. I don't want to screw this up. All right, and then I guess I could have rearranged that faster the other way, but whatever. Let me just double check. Q over MC. Oh, I should be adding this to the other side, something like that. Okay, apologies there. So now, what is delta T? Delta T in this problem is the hot reservoir, which was 100 degrees Celsius, minus this temperature. So in this case, when we plug that in, delta T should be, maybe I'll do this work over here. 100 minus this, that should be 80 degrees Celsius minus Q over MC. Is that showing up? It is. Okay. It's a little faint. All right. So that is our relationship for of delta T to the amount of heat you put in. So now I can actually use this result and plug that in, and notice we're going to get a differential equation. dq dt is equal to Ka over L times 80 degrees Celsius minus Q over MC. Great. At this point, let's think about what we know and what we're trying to find. Going back to the original problem, we were trying to learn about the length of the aluminum bar, and we know the total amount of heat required from part A, and we know how much time is in there. All right, so those are the kinds of things that we know. We know the mass, so we know the total time, not this time increment, and we know the total Q. So what we could do, and we're looking for L, everything else is constants that we know. We should do the integration, then we can get our limits involved, and after we get our limits involved, we could solve for L. If you want to pause the video and try it, good, go for it. I'm going to do it in 3, 2, 1. All right, what I would do first is actually factor out a negative MC for reasons that will hopefully become clear in a minute. Negative Ka over MCl times the quantity Q minus MC times 80 degrees C. Let me see if I did that right. If I factor out a negative MC on this side, I get the negative. I've got the MC in the basement. Now, in order to do that, I'd have to multiply this one by negative MC, and that's why I flip sign, this one flip sign. I like this because I can actually write this term right here as some heat, some amount of joules. It just makes it nice for me. Everything with Q, this has now units of joules. It's just easier for my brain to think about. Saves me a little bit of time in the integration. So, all right. We have basically two variables, Q and time. We know the limits of integration. We want to get those involved. So we're going to have to do something with this to integrate. Separate before you integrate. Get the Q's with the Q's and get the T's with the T's. If you want to pause the video, try that, and then maybe unpause the video and check that you did it the same as me before going on to the next step. 3, 2, 1. You cannot just add this stuff over. You got to get this whole term over here. This ends up being dq over q minus q0 equals negative ka over mcl dt. You might be sweating a little bit, freaking out about this minus sign. Don't worry. This term, mc times 80 degrees, is much bigger than this q, which was, I think, mc times 35.5 degrees Celsius. Oh boy, I've got a big sneeze. Let's see if I can get through this. Oh no. Let's keep rocking here. Anyways, the minus signs are going to work out, and you might be worried. Whoa! Sorry about that. Big sneeze. All right, so now we're going to integrate this, and this is what I was saying. We're integrating from 0 to q total, and we're going to integrate here from 0 to t total. And even though we don't know dq or dt, once we do the integral, we will know q total and t total, so we should be able to have everything in here except for L and solve for it. If you want to pause the video and crank through it, go for it. I'm going to solve it in 3, 2, 1. This integral becomes natural logarithm of q minus q naught absolute value. That's going to be pretty critical. Remember that q, we expect, is always less than q naught. Equals negative ka. We'll call this t over mcl, evaluated at 0. Whoops. Like that. If you want to just fast forward to the end, you can. I'm going to do this way. Oops, what was it? I think we call this T total, right? This was 0. This was Q tot. Now with the logarithms and the absolute values, hopefully you can see that this becomes logarithm, natural log, whatever, of Now, again, the minus sign. You're probably worried about this. The length should be a positive quantity. This is positive, 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 positive. This should be positive. Well, the logarithm can be negative, and in fact it will be. Q total was something like, I think it was 17.338 kilojoules, and I think this number ends up being something like, well, let's just do it really quick. I've got a calculator somewhere. There it is. It was 0.222 times, what was Q naught? It was this one. 0.222 times 2400 times 80, which is 42.624. So notice this term inside the logarithm becomes 17.338 divided by 42.624 minus 1, and then you absolute value that, and then you take the logarithm, natural, and I got this whole term, whoops, I get negative 0.522, something like that. Is that showing up on screen? Good. And so notice, this is what I was saying, the minus signs do work out. From there, what did I get? I think I found L is equal to 50.2 centimeters. Remarkably close to the result we got before. Okay, it was off, I think, in the third digit or fourth digit. I don't remember exactly. But yeah, so now if this situation was changing more rapidly, then our estimate might not be as accurate. So because this took place over a long period of time, this is approximately steady state at any point in time. You could almost call it quasi steady state. All right.